searching the voltages across the world, almost all of the American countries are around 120, and everyone else is at 220, 230.
Of course.
And then Japan is at 100.
Is it?
Yeah.
Okay. Interesting.
And everyone is at around 50
Hertz.
60 hertz.
Yeah. Let's find out. I don't know actually.
Well, I know a friend of my father that worked in like not high voltage, but like serious voltage, and he got electrocuted and survived. Has like a massive scar.
Really, what I don't understand is how people get struck by lightning and survive.
I think it depends a lot on, maybe what they're wearing too, and just look perhaps.
Let's check.
I know if you are in like an open field and there's lightning, you're supposed to crouch down on the ground.
Yeah, correct, yeah.
And put your heels together.
Yeah.
So that the electricity the current goes through your heels.
Huh, okay. Didn't know about the heels.
Go through, through your entire body.
Interesting. Alright, we'll continue now, guys. How many did you get done, Dorian?
6.
Great. And Gina? 6 as well. Great. Alright. We'll continue. Can you write that down? Coulomb's law next.
Related to immediate medical attention.
Yeah, if you get struck by lightning, immediate medical attention, yeah. Or a funeral director. You'll need one of them.
The amount of current moving through the body is also a factor.
Yeah.
So
Yeah.
What happens when a person spontaneously combusts?
No, that's not a real thing. That's a fake, a ghost is having my baby type of aliens came to visit me stuff.
There was a case in Ireland.
Of what?
The police ruled as spontaneous.
Who said this?
The coroner.
Who said this?
BBC.
Marine showed us.
I don't know what trash newspaper she's showing you.
BBC.
BBC?
Yeah.
Really?
Yes. And then we researched more, and then around the world there's more than 200 these kind of cases.
Around the world.
It's just always interesting that the spontaneous combustion happens to elderly people sitting in their chair in front of a fire. No, seriously,
Yeah.
It's never like somebody just walking through the shop and...
Or
But
someone.
they said that the more logical thing is could be they were smoking, they were lighting something, but then they got burned, so you don't know that they lit themselves up. Because it gets burned in the...
I don't think spontaneous combustion's a thing.
Well, we need a lot of.
They got smited by God.
Yeah. Yeah. I really don't think it's a thing.
I thought, it has something to do with your neurons going and your internal electricity system going haywire.
No.
No?
No. It's always somebody, it's like you said, like maybe someone smoking or somebody sitting in front of a fire.
But they said that the fire was not the cause,
Yeah, that's
and
right.
there was no accelerant found, no trace.
I don't buy it. Right, Coulomb's law. Have you got that?
Yeah.
Yep. So, remember that a point charge will produce an electric field. So let's have a look at the force of attraction or repulsion between these charges.
It's the same as the gravitational.
It would be, wouldn't it? So if you have a charge here of Q1 and a charge here of Q2, and let's just keep them opposite charges. So this one gets pulled towards this, because what will happen is this will have a field. And you remember we said the formula for the strength of the field is 1 over 4 pi epsilon 0 q1 over r squared. But F equals EQ. If you put those two formulas together, you get this formula. F is 1 over 4 pi epsilon 0 q1 q2 over r squared. And quite often people just call this a constant k. So you get F equals k q1 q2 over r squared. So you don't really need the proof, but that's Coulomb's law, where F is the force between the charges, R is the distance, and K is a constant. And I've calculated for you, it's 8.99 times 10 to the 9. And the units are Newton meter squared per Coulomb squared.
So is each charge pulling on each
Yep,
other with
yep,
the force
yep,
F?
symmetric, yep.
Okay. And vice versa, it could be repulsion. if
Yep,
they're the same.
Yep, yep. Okay, you got that? Okay.
It's the
Mm-hmm.
same for the gravitational thing, right? Just the gravitational cluster.
Mm-hmm.
How do they calculate that cluster?
There's experiments for calculating it. In fact, there's even an experiment where you just have two giant lead spheres and measure the force between them. Calculating the G is actually the hardest constant to calculate. It's the one with the most error. Speed of light and constants like this, very well known. Big G, not as well known. Okay, continue. Yeah. Now you can still use the 1 over 4 pi epsilon 0, but that value of k, that's given in the formula book if you want to use that instead. Okay. Right, continuing. So, yes, Diego? Yeah. Let's examine how Coulomb's law applies here. There's a force between the proton and the electron, attraction or repulsion. Attraction. If the forces are the same, then why does the electron move and not the proton? Why is it this way around and not the other way around? If the force pulling on the electron is the same as the force pulling on the proton, why is it this way around and not the other way around? It's because of the mass, isn't it? The proton is much bigger than the electron. So it's the electron that orbits the proton. So even though the forces are the same, the masses aren't. And so it makes it look like the electron is pulled towards the proton. But we should also remember that the proton is being pulled towards the electron. It's only the difference in the mass that makes the picture the way it is. Okay. So we talked about the mass. So although the forces are equal, we often ignore the force on the proton because it's not really moving much. So we just pretend there's the force pulling on the electron. Okay? But it is worth remembering that there's equal forces here. Okay? So in fact, the proton isn't stationary. what's happening is the electron is going around the proton, and the proton's kind of wiggling, because the electron is pulling on it as it moves around. Okay, you can actually measure this wiggle. You can see it. Okay, so the electron is trapped, right? So it has potential energy. Will it be positive or negative? Yep. When one charge q is trapped in an orbit by another charge q, then it will have negative potential energy. Now, my formula is a little bit confusing. I'm using q's here to only be positive, and so I put the minus in here to force the answer to be minus. But if you realise, if you let one of the q's be positive and one of the q's be negative, then it'll be negative anyways. So perhaps to prevent any type of confusion, I'll say the potential energy, when it's trapped, is equal to minus k q1 q2 over r. Okay, this is when you have a q1, and then here you have a q2, which is usually smaller, like an electron, and it's trapped in an orbit. Now this is important for chemistry. Does anyone know what this potential energy formula represents in chemistry? Kinda. Something else you did in semester 1. No. It's the ionization energy level. To remove an electron, yeah. The electron has negative potential. For example, suppose the electron had minus 2 joules. Then how much energy is required to give it 0 joules if it has minus 2? 2. So that's the energy you need to free it. Because remember we said when the energy is 0, we describe it as being free. So this formula calculates the ionization energy, the energy required to free the electron from its orbit. So that's very useful in chemistry, okay? So you want to write this down.
So it's R.
Say again, Dorian?
Just R.
Yeah, not r squared, yeah.
That's the radius of
This is between the centres.
orbit.
Yeah, the orbit, yeah.
That also suggests the radius, the orbit is circular.
Yep.
Which it's not.
Yeah, so you can approximate it as a average circular radius. It can be elliptical, it can be different shapes.
And there's perhaps more than one electron.
Yeah. This is a simplistic model. We're imagining the electron moves in a circle around the proton.
What is a single hydrogen called?
Bohr's atom,
What was that?
isn't it? Bohr's model. That's the single proton and the single electron. Right, you got that? Yeah, okay. So, Coulomb's law gives the size of the force between two charges. This force between charges is actually one of the 4 forces of nature. There's 4 forces in nature. Also, Coulomb's law is an example of what's called an inverse square law in physics, and these are quite common. It's worth examining why. So, I want to give you an example. Do you see in Coulomb's law, you have this r squared here in the denominator. That's actually very common in physics, and I'll show you why it's so common. So, imagine you're measuring the smell of someone. Okay, so you have some unit, let's call it smelly units, or what would we call it? Stink units, yeah, stink units or something like that. Okay. Now, here you put your detector, and here you put your detector. So maybe this person is giving off 1 stink unit per 1 second, for example. Okay. Which detector will detect more of it? The one nearer. What you kind of need to imagine is there's almost like there's a sphere, and the stink units get spread across the sphere. But as it expands outwards, what is happening to the radius of the sphere? It gets bigger. So the same amount is getting spread over a bigger area. Yep. So you could say, okay, here that is 1 stink unit per area, and here that's 1 stink unit per area, and this is 1 stink unit per area. But what's the formula for the area of a sphere? 4 pi r squared. So this is like 1 stink unit over 4 pi r squared. Now do you remember earlier we had 1 over 4 pi epsilon 0? So there's the 4 pi, and there's the r squared. So basically in physics, these formulas are common whenever you have something spreading out in a sphere. You get formulas like this. This is kind of how people come up with these formulas to begin with. They kind of imagine, okay, there's something that's coming out of the electron, but whatever it is, it must be getting spread out over a bigger area. So it must diminish proportionally to 1 over r squared. Yeah. That's the volume. Yeah. Anyways, you don't need to write that down. It's just worth examining why. We'll see this quite a bit in physics. Finally, it's worth noting that the value of k, what was it, 8.99? Yeah, that's extremely large constant in a formula like this. It's extremely large. Because think about what that's saying. If you had 1 Coulomb and 1 Coulomb, 1 meter apart, I don't have my meter stick, how much force is that according to the Coulomb's formula? Look at the formula.
8.99 times
Yeah.
10 to the 9.
Yeah, look here. K, Q1, Q2 over r squared, okay? So imagine you have 1 Coulomb, and 1 meter. What's the force? It'll be the K, won't it? Because they're all 1. That's a huge force, isn't it? What did we say? 8.99 times 9 newtons. That's extremely big force, okay? So it is worth pointing out that in the formula the K is unusually large. Yeah? Yeah. Okay.
So what's the prefix for 10 to the 9?
Mega is giga. Giganewtons. Giganewtons. Right. Quick calculation for you. Tell me the force between the proton and the electron when it's 0.1 nanometers apart. Yeah, you'll have to, do you not have your Casio calculator or has the E constant on it?
Oh yeah, both of them. I know it's not great.
E is a charge of the electron.
Yeah, which is also the same as a proton.
Is it this thing, micro P?
No. Huh? What are you talking about, man? It's like constant E. It's like 23 or 27.
No, like charge of the proton.
Huh? No. It's just E. Zach, it's just E.
What was the actual figure of it? Or chapter? No, I know, but I have the list here. I can't figure out which one.
This is small k, is it the same?
No, that's Boltzmann's constant. You can type it in manually, Zach. 8.99 times 10 to the 9. Did you get an answer?
Right now it's negative.
Right, I'm not too worried about the sign because I just want the size of the force of attraction. So, the answer is F equals 8.99 times 10 to the 9, wasn't it? Times the E constant times the E constant over 0.1 times 10 to the minus 9 squared. What do you get? Small number.
2 point. No, it's not small.
Was it?
2.8.
Yeah.
Times 10 to the 11.
So that big?
Huh? I got 2.3 times 10 to the
2.3 times 10 to the...
Negative 8.
Are you using the right E constant? What number is it on your lid? On your lid?
23.
And you use that?
Yeah.
Do you use minus 9 here?
Oh, minus. No, I use minus 9.
You just
Yes.
did you use 2e or e times e?
2e.
But E times E is E squared, Zach. Alright, continue? Continue? Yep. Right. How long does it take an electron to orbit a proton if the radius is 0.2? Yeah, the time. What's the time for the electron to go around the proton? Electron, proton, distance between them is 0.2
Well, the electron
nanometers. I want the time.
Do you have a circular motion?
the electron radius, if you want.
We all have it. It's 0.2.
0.2817. What's a muon?
What's a what?
Muon.
A what?
M-U-O-N.
M-U-O... Muon.
Muon.
Ah, they're subatomic particles. You don't need to worry about those guys.
No, I know, but it's just on my list of values. So.
Don't worry about those. Don't worry about those. Did you get it? Zach?
I remember the form.
Circular motions?
Yeah.
It's a problem. T equals? Oh, yeah, but it's not. Yeah. How can you get omega? How can you get phi? And, okay. Oh, look at you all checking your notes like you're pretending you forgot. How do you forget so much? How?
Too many brain damages.
It's just. Well, we do it. Yeah, okay. So look. T equals 2 pi over omega. Okay? But remember, what do we say? F equals ma, which equals m v squared over r. And also, as you said, Lynn, v equals omega r. Okay, so what you could do, you could change this into 2 pi over v over r. That's 2 pi r over v. Great, we need to figure out the v. So we can look at this formula. We can say v equals, v squared equals fr over m. Yeah? So that means this is 2 pi r, and the v will be root m over fr, because it's upside down. Okay? So this is 2 pi, we know, r we know, m we know, r we know. Do we know the f? We can get the f. How can we get the f? Coulomb's law. But it's upside down. So that's 1 over k, or squared, over q1, q2. So finally, the answer is 2 pi r root m r over k q1, q2. Okay, I've been a little cruel to you. It is quite hard, but I think it's possible to do. So this will be 2 pi times 0.2 times 10 to the minus 9 root mass of the electron times 0.2 times 10 to the minus 9 over 8.99 times 10 to the 9 times E squared. Yeah, are you sure?
Yeah, just says 0.
Mm. What did you get, Lynn?
1.11
Yeah.
times 10 of negative 15.
Oh, never mind, I had a 0 in it.
That would explain it.
What's the value of E? Because I can't find it here. Do you know the value?
It's on the. You have it in your notes.
Yeah, well,
69.420.
16.
No, it's not. Don't it, he's just making a number up. Here.
Is it 1911?
Times 10 to the minus.
9.11.
Times 10 to the minus what?
31.
31. Wait. Is that. No, that's the mass, isn't it? What? No, he wants the charge.
On charge is minus 1.6 times 10. Minus
Don't put in the minus. 1.6 times. Well, it doesn't matter. 1.6 times what?
Times negative 19.
Minus 19, okay.
So E to the minus.
What's off the map?
Pico? Not sure. Don't that usually go there?
And 15.
Pico, is it?
Pico and then what after?
Femto?
Pento?
Femto.
Femto.
Or maybe I had that backwards. Pico, femto? Don't know.
So it's 1.6
Then it's Pikachu, and Raichu. Okay. Is that okay, guys? I know that was a hard one, but is it okay or not?
I would have been able to do it if I had my formula sheet.
Okay. You would have gotten away with it too if it wasn't for those pesky kids, huh? Okay. So transformer lesson was easy, but now we're back to a little bit of a tricky one. How many questions are there in the Coulomb's lesson? Oh, that's okay. Right, can you get a start on those 6 now? Yeah. Is okay, Gina? Is the answer right? Okay. I can trust Lynn.